talking about how to find equations of planes in three-dimensional space. So these have the form ax plus by plus cz is equal to d. You may have had a couple of questions. A couple of questions perhaps would be, number one is, why is this the equation of a plane? So as we talked about before, ax plus by is equal to d. This looks ahead in R2. This is a line in R2. This is a plane in R3. So we know this is a line in R2 from high school algebra class and stuff like that. But why does this kind of equation give us a plane R3? That's one natural question to ask. Another natural question to ask is, well, we know that there's a certain form of how to write down an equation of a plane R3. So we know that if I give you a point and a direction vector, so if their point is x naught, y naught, z naught, and if our normal vector is capital A, capital B, capital C, we know that the equation for the plane is a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. So two questions to ask here. Number one, why is this the equation of a plane? And number two, why is it that if we have, this point and this normal vector, why is this the exact recipe that will give us an equation of a plane? And so this video is going to try to examine similarities between this form of an equation for lines in R2 and this form of equation for planes in R3 to show you that there's good overlap between the two and to help motivate and help justify why these two equations are the way they should be. So for starters, let's take a look at just in lines in R2. So for the next little bit, all we're going to be doing is discussing lines in R2. So perhaps here is a very simple equation for a very simple line. Y is equal to 2x plus 1. So it's written in slope-intercept form. So we see here the slope is 2. We see that the y-intercept is 1. So we want to, without too much difficulty, we can graph it. Maybe we should make it look more like the form that was on our previous slide. So minus 2x plus y is equal to 1. So now that matches up what we have here. So a would be minus 2 here, b would be plus 1, d would be plus 1. So this is in, I think the term here is standard form. So this is a different equation for the line. Now, let's talk about what's going on here with direction vectors. So we could think about that along this line, that we have a direction vector. The vector 1, 2 points along this line. So that means as we go to the left 1, we go up 2 units because, well, what's our slope is? Slope is positive 2. So direction vector over 1 up 2, direction vector would be 1, 2. So now, well, we could ask ourselves, what's a vector that is orthogonal, perpendicular, normal to our line? Well, if we wanted this to be normal, to be orthogonal, we could achieve that by going minus 2, 1. And we're going in the minus 2, 1 direction. So note the dot product here. 1 times minus 2 plus 2 times 1, that dot product is 0. So these two vectors are orthogonal to each other. Well, minus 2, 1, have we seen this before? Well, yes, we have. Take a look at what the coefficients of x and y are in our standard form over here. The coefficients are minus 2 and 1. And so we see here that just like in the equation for the plane where the entries in our normal vector give us the coefficients of x, y, and z. So I give you like the normal vector components A, B, C. You use those as A, B, and C here. We see that this also works in 2 dimensions for lines. You give me the components of a orthogonal vector, a perpendicular vector to your line, and I'm going to use those as the coefficients over here. So that is one similarity that helps justify. I said there are kind of a couple of things here. Why this form? So we can see here that A and B give us the normal vector for a line R3, just like ABC gives us a normal vector to a plane in R. I think I said R2 for the line, or R2. Sorry, I said R3 for a line. So AB gives us normal vector for a line in R2. ABC gives us the normal vector for a plane in R3. But we can do even more. Let's see what we can do with, so we know our normal vector for the line is -2, 1. And we can realize that the point 1, 3 is on the line. So guess what? We can combine that information together in the same exact way that we did for the planes to come up with an equation for the line. So we can say here that -2 times x minus the x coordinate of the point that we have, plus 1, the entry from the normal vector, times y minus the y coordinate of the point we have, is equal to 0. So that's the same exact, that's the equivalent of this version here of this equation. And let's see that if we take this equation and we split it up, we get -2x plus 2 plus y minus 3 is equal to 0. Plus 2 minus 3, that's -1. Minus 2x plus y minus 1 is equal to 0. Rearrange, what do we get? Y is equal to 2x plus 1, which is exactly the same thing as what we started with. So this shows that there is good reason for in being inspired by what's going on in lines in R2. There's really good reason to have ABC, to use the coefficients of the normal vector there when we're coming up with an equation for a plane. And moreover, it makes sense that this particular way of using our particular point to find the equation of the plane makes sense by analogy with this in R2.